Okay, so as we head into this new module, the focus is going to be looking at data and figuring out probability and then predicting stuff from that probability, trying to interpret that and see what that means for us. So there's not a whole lot of computational stuff. It's more of, hey, can we predict what is the data saying about certain events? All right, so what we have here is this little introduction in your workbook says tuberculosis, which short for is TB, can be tested in a variety of ways, including a skin test. If a person has TB antibodies, then they are considered to have TB. Below is a tree diagram representing data based on 1,000 people who have been given a skin test for TB. So some of you, or a good portion of you, how many of you guys have had a TB test? Okay. It's the one where they put the little shot just underneath your skin, creates a little bump, and then you have to go back a couple days later and get it checked. Okay, so a lot of you have had it. It's not a big deal for the test. And they just go back and check it, and then it's positive or negative. So what we have here is we have a tree diagram. The reason they call it a tree diagram, kind of looks like branches. It's branching out from where it goes, and it gets more specific as you go out from there. So as you can see, there's two groups initially. There are the patients that have TB and the patients that do not have TB. So this is kind of a known fact. And then we look at, they get tested. Some of them then return a positive or a negative test. And so what I want you to do is write two probability statements about the test. Okay, so some prediction, some probability that happens. You're going to type this right onto this slide. Okay, so again, 620 out of 1,000 don't have TB. We have the converse, 380 out of 1,000 do have TB. So talking about the same, add those together, we get our 1,000. Those are probabilities, just comparing rates of numbers. Okay, there's several others in there, but I just want us to initially get to see what a probability statement kind of looks like. There's this idea within probability. It's called conditional probability. And what conditional probability is there's a condition that's set first, and then we figure out the probability after that. So the probability of an event happening given another event already happened. So in this case, the one example I give you, what is the percent of people who test positive given they have TB? So the condition is they have TB. So we're looking at that group there. So the bottom half of that tree diagram we don't even pay attention to. We're just paying attention to the top part, the one that comes off of they have TB, because we already said that's what we're worried about. So how many test positive given they already have TB? 361. So that's our conditional statement. 361 out of 380. You divide those, that would give you the percentage. My condition was they have TB. My question then after that was how many of them test positive. If I didn't put the condition, then it would be 361 out of 1,000 out of the whole thing. So a condition breaks it down into even a smaller group. So here's what I want you to do. I want you to add a slide, because there's not a lot of room to type on this one. I want you to add a slide, and I want you to write two more conditional statements and then determine the probability of those conditional statements. There's actually three more. I'm only asking you to do two. All right. Now, who would like to share one of their other conditional statements? Ignacio?
What is the percent of the people who test negative given they don't have TB?
Okay, so test negative given they don't have TB. Good. And what'd you get for the ratio or the probability on that one?
I divided 19 by 380 and I got 5%.
19?
Yeah. Divided by 380 and I got 5%.
Wait, maybe I misunderstood. Did you say they tested negative and have TB?
Yeah. No, they tested negative and don't have positive.
Yeah, so tested negative, and they don't have TB. So which group doesn't have TB? That's our, yeah, that'd be 558 out of 620. Okay, because the ones who don't are down there at the bottom. All right, someone else who has another one.
I said, what is the percent of people who test negative, given that they do have TB?
Good. So another one is tests negative, given that they do have TB. And so what's that?
19 out of 380.
Out of 380. And then the last and final one that we could do was, what's the percentage of people that tested positive but do not have TB? So you understand those conditional statements now determine which branch we choose on our tree diagram. Here, on the bottom it says patients that do not have TB. 620 of them do not have TB. 558 of them tested correctly that they don't have TB. So I go in, I get tested. I don't have TB, I get tested. The test tells me I don't have TB, I'm good. The other case, I go in, I get tested. I don't have TB, but the test says I do have TB. Now I have to worry, do I actually have TB? Here's what happens. So I'm one of those 62. I go back in later and I get tested again. And the likelihood of me testing positive again is so small because what was our percentage? Our percentage was less than 1%. So being in that less than 1% of a wrong test twice in a row is crazy small. And so if you get tested twice and you get it positive both times, what's that probably mean? That you have it. Okay. Now they have other tests to confirm after, but this first initial test is a simple test. So part of understanding the world around us is being able to take information, make sense of it, and then explain it to others. Based on your statements above, what would you say to a friend regarding the validity of their results if they are testing for TB and only get a skin test? Be sure to use data to best inform your friend. So here's what you want to do. Your friend's getting tested. Would you tell them to trust the results or not based on the data we just saw? So you're going to write a little response like you're explaining to your friend, and then you have to give reason, and the reason has to be backed up based on actual numerical data. Okay, so just don't say, oh, I won't trust it because doctors are crazy. Okay? You need to have mathematical data behind that supports your statement. Hey, I'll give you a couple minutes to work on that. Our Jenny says don't trust it because it's not 100% positive. Jonathan is saying trust it because of those who don't have TB, majority of them tested not to have TB. All right, Julio, what do you got to add?
Tested it on other people and nothing came to them. Nothing will come no harm to you just by knowing.
Correct, but would you trust the results of the test?
Well, yeah.
Okay, why? What's the math behind it that you would support that statement?
Well, it shows that the out of to be a pretty good number.
Yeah, so if we look at this total, we have 1,000 people that were tested. How many of them were wrong tests? So in our Jenny's case, there were 19.
Yeah, it was 19.
And then Jonathan talked about the ones who don't have. There's 62. So total, there are 81 out of 1,000 that were incorrect.
It could be that 81.
You could be that 81, but what is that percentage? It's 0.81%. Less than 1% of the time, they're incorrect, which means more than 99% of the time, this test is correct. So I would say I would trust this test.
Be that 81 person.
if your friend is like, what if your friend is a person, like, having trust with him?
Okay, so a false positive, all it means is an error in the data reporting in which a test results improperly indicate presence of a condition. So a false positive was the ones where you didn't have TB, and they said you did. Those were the 62 people there. Okay, so it was wrong, that's why it's false, and they falsely said you're positive. False negative is the opposite, where you actually have the condition, but then the test says you don't. And in this case, it was 19, a much smaller percentage. Okay, so that's what a false positive and false negative. You have these in testings all the time, especially with medical stuff. Okay, so knowing those terminologies will help us moving forward. So here's what I want you to do. Based on these, and I kind of already talked about what they were, I want you to write in on this slide, where is there a false positive and where is there a false negative? So explain to me where those two fall within that tree diagram. And then once you have that typed in, you're going to put Chromebooks up. We'll be done for the day at this point. So where is there a false positive? What grouping? Okay, so in the lower branch, it splits into two. So which of those two? Okay, so yeah, so the false positive is one where there's 62 people. And really what that states is they tested positive, but in reality, the patient doesn't have TB. Okay, good. Someone else. Where's the false negative located at, Esteban? Okay, so there's 19 of them. And that is correct. So they're tested negative. Test said they don't have it, but in reality, the patient does have. Let's talk through some of this situation. So in this situation with TB, explain the consequences of errors. So those are the false positive and false negatives that we talked about yesterday. So let's talk about a false positive. And someone remind me, what's a false positive? Austin?
They say you have the disease and you don't.
Correct. So false positive, you tested positive, but it was false, which means you incorrectly tested positive. So they said you have TB, but you actually don't. So what are some consequences of having that? Julio?
So you could be spending money that you don't have to spend on medical.
Okay, good. Money and time on unneeded medical, on unneeded treatment. Okay, what else? Austin?
Unneeded isolation and stuff to keep others healthy.
Okay. Okay, and then there was a good one from my last class. They said loss of job opportunity.
Why?
Because some jobs you can't have TB. And so if you have TB, they can't hire you because of whatever that specific job is. And so if you had a false positive, they'd say, well, sorry, you can't hire you, which sucks because you actually don't have TB, but the test says you do. So, I mean, kind of with the money and time on unneeded treatment, part of that may be going and getting tested again, but that's still time and money that you're spending. Yeah, even though if it finally comes out that you don't have it, which is still nice in the end, it still is not as good because you spent that extra time. Now, let's flip it and let's talk about a false negative. So a false negative again is what?
So you don't have it.
Yeah, they say you don't have it, but you actually do have it. So what are some consequences of that? Hold on.
You could
Wait.
go on living and then like get sick and die and then you couldn't.
Yeah, you can go untreated, right? Which then could lead to more health problems and potential death. Okay? Ignacio, do you have something else? Yeah, you could unknowingly infect people.
You can work.
You could work, but that's kind of a good consequence, right? But these are pretty serious because you could go and some of this means, because some of the symptoms are like a cough and trouble breathing, so you may go in the doctor, you tested that you didn't have TB, so they may believe, oh, he doesn't have that, and now they're just treating you maybe for a common cold. So you may be getting treatment that you don't need.
Hola.
Number 4, how would you answer the young adult who tested positive and asked, do I really have TB? So what you need to do is go back and look at the tree diagram. As you look at the tree diagram, how often is there a false positive? What's the odds of a false positive? How many false positives were there? 62 false positives out of how many total people? How many total people were tested? 1,000, right? Because that tree diagram, the initial ones tell us if they have it or not. But if this young adult's walking in, we don't know if they have it or not. That's why they're getting tested, correct? So they're walking in getting tested. So they're one of 1,000 people that come in. We don't know if they have TB or not, and they get tested and it comes back positive. Well, the options are, there are 2 of them. It could be positive and they have TB, right? Or it could be positive and not have TB, in that case, a false positive. Well, the odds of having a false positive are 62 out of 1,000, which if we break that down to a percent, is 0.62%. So what is the likelihood that it was a false positive? Yeah, crazy small. So you can tell them, yeah, there is a chance that you don't have it, but the likelihood is what? Yeah, you do have it. So that's how you use data to support that statement. Is I would state, okay, there is a small chance. It's a 0.62% chance that it was a false positive. But that being such a small percentage, the likelihood is that you do have TB. To find out more, you can go get tested again, because to get a false positive twice is so crazy small that it's almost non-existent. The way that would be is it'd be 0.62 times 0.62, which is a crazy small. So it'd be 0.0036 or something like that. All right, so crazy small, less than 1% of 1% type deal. So with that, hopefully those help you answer. I want you to answer all of those 4 questions there.